All right, so this is going to be my next video. So we're working on problem 3 today. I promise the videos will get a little bit better. I'm honestly just getting a little used to kind of the setup that I have going on here, and then also, I might be like a little bit shy on camera, but I promise they'll be a little bit better. The introductions won't be as long. I'm just gonna go ahead and jump right into the proof. So the question we're going to have today, we are working on question number 3 from this problem set. So it says, let G be a finite group of odd order. We want to show that every element has a unique square root. That is, for any element in G, there exists another element A, such that when you square A, you get G. So there's two things we need to show here. So one, we need to show the existence of the square root. And then after we show the existence, we need to show that it is unique. So this will be a two-part or like two-step type of proof. Okay, so let's go ahead and get started. So the proof for this, this one's a little bit longer, just because there's a few things we need to show. So let's start with our assumptions. So we're going to let G be a finite group. And we know that this group is of odd order. So let G be a finite group of odd order. So since we know that G is a group of odd order, we can actually say something about or find a way to express the order of G. So we can write the order of G as the multiple of some even number plus 1. Here, we're going to define n to be some integer. So usually with these types of proofs, especially when you're showing like existence of something, you kind of already have to have an idea when you're writing your proof. Like you kind of do this like as your scratch work or something. You already know what the element is supposed to be, but like when I was working on this myself, I kind of had to play around with a few things in order to make it work in a sense, right? It's one of those things that with existence, you just kind of have to find it. So we're going to define A to be the element G to the n plus 1. And so I'm claiming that A, this element that I just defined, I'm claiming that this is actually going to be the square root, which is why I kind of named it A. So what I want to show is that if I take A and I square it, I want to show that A squared is equal to G. So let's go ahead and get started. So A squared is going to be G to the n plus 1, and then this is being squared. And then properties of exponents is going to lead me to G to the 2n plus 2. And again, further properties of exponents, I'm going to split this up, and this is going to be G to the 2n plus 1 times G. And since the group G has order 2n plus 1, we know that in a group, if you raise any element to the order of the group, you end up with the identity element. So this is actually equal to the identity element times G, which is just going to be G. So this proves the existence of the square root. This element that I just defined here is going to be that square root. Now what I want to do next is show that this element that I defined is actually unique. It's the only one. And so we're going to show the uniqueness part now. The approach to showing that anything is ever unique is you're going to suppose that there's more than one, and you're going to argue or demonstrate that those two different elements or whatever they happen to be in the context of your problem, you're going to argue that they were actually the same thing to start with, and that'll show the uniqueness part. Now for the second part, for the uniqueness, we're going to suppose that there are two elements that or two square roots that do the same thing. So suppose that A squared is the same as B squared, which is going to be the same as G, where A and B are just two other elements in the group G. So where A and B are elements of G. And now we're going to consider the elements. So we're going to operate A and B inverse. So consider A times B inverse, and we're going to square this. This element here. Again, the goal we're after is we're trying to show that A and B, these two elements, are actually the same element. So when we square this is going to give me A to the second power times B to the negative 2 power, like B inverse squared, which is going to be A squared times B squared inverse, which will give me A squared is equal to G, so this is going to be G. And then B squared is also going to be G, so this is going to be G inverse. And this is going to give me the identity element here. And so what this is going to tell us is that the element AB inverse has order that divides 2. It doesn't necessarily have to be 2. We have to remember two things from Lagrange's theorem. One is that the order of any element divides the order of the group. And then more generally, if you take an element and you raise it to a power, which in this case is 2, we raise it to the power 2 and you get the identity element, then the order of that element divides that power. So the order of AB inverse doesn't necessarily have to be 2. And actually it can't, because since the order of the elements needs to divide the order of the group, and the order of the group is odd, 2 doesn't divide an odd number, the order of AB inverse cannot be 2. So the only other number that divides 2 is going to be 1. But what's interesting about that is that the only elements that has order 1 in any group is the identity element. So I'll try to write this out very briefly because I know I just said a lot and I don't want to write everything out. What this tells us is that the order of AB inverse must divide 2. So the two options are the order of AB inverse is equal to 2, or the order of AB inverse is equal to 1, which gives us that AB inverse as the identity element. And again, we just talked about why it can't be this choice here, because the order of AB inverse has to divide the order of the group, and we have a group of odd order. So that can't happen. So it has to be the second option, which leaves us with AB inverse equaling the identity element. Now, if we apply B to the right on both sides of the equation here, it leaves us with, so let's check this one off. Thus, it leaves us with A equaling to B, which proves the uniqueness part. So the square root does exist, the square root is unique, and this completes the proof. So this completes the proof. And we'll stop here for this proof. And so the last thing I want to do now is just give an example. So usually after the proofs, I'll try to provide like an example that is relevant to the proof to kind of demonstrate how it works. So the example that I want to do today, I usually like to work with the integers modulo something, just because they're kind of nice to work with. So for this example, I want to work with the integers mod 5. So the integers mod 5 consists of the elements 0, 1, 2, 3, and 4. So this is a group of odd order, so this one has order 5. And the theorem claims that every element in this group has a unique square root, right? So that is, the theorem says for any, we'll say G in the integers mod 5, there exists a unique A in this group such that when you square A, such that A squared is equal to G. So kind of like we did in the proof, let's define what this A looks like. So in the integers mod 5, A squared would be like multiplying by 2, right? So in this context, my A squared looks like what my A squared equaling G is reading. It's reading that 2A is congruent to G mod 5. And so what I want to do now is try to find what that A is. So kind of like we did in the proof up here, we defined A to be G to the n plus 1. I want to do something similar with A here. I want to define what it is. So I want to cancel out that 2 on the left. Now you might be tempted to want to divide by 2, just because when you equation solve and the 2 here is like technically multiplying by 2, but it doesn't necessarily work that way with modular arithmetic. So we need to apply the inverse of 2 on the left on both sides of the congruence. So the inverse of 2 in the integers mod 5 is going to be 3, because if you do 2 times 3, that's going to give you 6, and 6 is congruent to 1 modulo 5, where 1 is the identity element in the integers mod 5. So to cancel out that 2, we're going to multiply by 3 on the left side. So this gives us the following congruence. A is congruent to 3 G mod 5. And so what this congruence is telling us is that if we want to find the unique square root for any element in the integers mod 5, then all we have to do is compute this part here. Now for the uniqueness part, I mean, we did the proof already, but you could also check the rest of the elements yourself, and you would see that every element has a unique square root. So when you go to check these, there's not going to be an element that has more than one square root. If you list these out like in a tabular form or something, you'd see that for yourself. But for the example that I'm going to do, if I want to know what the square root of 3 is, then I will just do, so we'll say for 3 in the integers mod 5, the unique square root is going to be this a here, which is going to be 3 times 3, which is going to be 9, which is congruent to 4 mod 5. So the unique square root of 3 in the integers mod 5 is going to be 4, because if we do 4 squared, that's going to be 8, which is going to be congruent to 3 mod 5. And so to close out this video, I just want to say a few remarks, mostly on why the odd order matters. So this whole result relies on the group having odd order. And that's literally what's carrying like the entire uniqueness part of the proof. Because if 2 square roots existed, then their quotient would square to the identity, meaning it would have order 2. And we saw that in the proof when we were writing this out. But since we're in a group of odd order, the only element with order dividing 2 is the identity itself. So those 2 roots had to be equal, as we saw in the proof. But what ends up happening, like when you give up that odd order, like take for example a group of even order. Let's take the multiplicative group of the integers mod 4. So this group consists of the elements 1 and 3. You lose the uniqueness part because the element 2 has 2 square roots. It has 1, it acts as its own square root because 1 squared is 1, but then it also has a square root of 3 because 3 squared is equal to 9, which is congruent to 1 modulo 4. So the moment you give up that odd order of the group, you give up the uniqueness of the square roots. Another neat point is that the group doesn't need to be abelian. So if you notice in the proof itself, we didn't mention anything about commutativity of the elements. We only used like basic group axioms and the fact that the order was odd. And so that's all I have for this video. I'm going to try to upload another one probably sometime over the weekend. So if you're enjoying these videos, then I hope to see you in the next one.